the base of solid S is a circle, radius 5 inches. Cross sections perpendicular to, it actually doesn't matter which axis, but if you have a choice, usually picking the x-axis is the easier one to be perpendicular to. So cross sections perpendicular to the x-axis are rectangles whose height is 1/2 the base.
Well, it just gave us the width was.
Okay, so same difference, right?
Yeah.
Cool. So it looks something like this. So I'm gonna draw my circle. And I'm gonna think about a little cross section right here. And that line right there is representative of the base of one of my rectangles. So I'm imagining a rectangle popping out of it like that. And technically it's got a little bit of thickness to it, so it really looks more like this. And not that you need to draw this picture, just it's helpful to me kind of see it. There's one of my rectangular slices or slabs. So the volume of my slice is going to equal base times height times thickness, which is dx. The base is this length here. The height is half that. So whatever this length is, we know it's going to be our length times half our length times dx. So we have to figure out the length is, but the length is just the top function minus the bottom function. But our length is the top minus the bottom. We know that, well, we could write the equation, right? The equation of the circle is x squared plus y squared equals 25. Solving for y, we get y equal to plus or minus the square root of 25 minus x squared. So then the top is the plus part, the bottom is the minus part, and the top minus the bottom is going to be 2 times the square root of 25 minus x squared. So then we throw that into our formula. We're going to get, I'm going to pull the 1/2 out in front. All right, it has 1/2 times that again. So times 2 square root of 25 minus x squared, quantity squared. Right? Right? Well, I may have to say more to myself than to you guys, right? Yeah, right. And then the total volume is going to be the integral from as far left as -5 to as far right as +5. I'm going to simplify this a bit. It's going to be 1/2 times 2 squared times the square root squared. That isn't too terrible. This simplifies as 2 times the integral from -5 to 5, 25 minus x squared. We integrate, we get 2 times 25x minus x cubed over 3 from -5 to 5. That's going to end up being 2 times 125 minus 125 thirds. And then subtract the same thing essentially. Minus -125 plus 125 thirds. I always say this to myself, when you have something minus a third of itself, you're left with 2/3 of that thing. So I have 2/3 of 125 plus another 2/3 of 125, right? Because these aren't going to cancel out, they're going to add together. So I have 2 times 4/3 times 125, which is 1,000 over 3. Seem good? Cool. Hopefully you got somewhere close to that on your exam, assuming we have reconstructed the question correctly. So I'll say, any questions about this? Good. I see people looking like they're feeling good about it, so hopefully it went well yesterday. Before we start talking about first order linear differential equations again, are there any other questions from your exam yesterday that we could address? Yeah, Jennifer. Again, I don't know the exam, so you have to describe it specifically to me.
the population.
So the population is proportional to the rate, or the rate is proportional to the population? I guess okay.
Like, it was broken down into multiple, like, there was that first one, and then they said that the limit was, or the capacity was 5,000.
Okay.
And then we added to it and said the minimum was 500.
I think like, why don't you turn the base one and then change it?
Yeah, change it as the.
Okay.
But like, do you know the basic one? And then he kept asking for what was per capita.
I mean, my guess would be it's something like dn dt is equal to n times 1 minus n over, you said 5,000?
Yeah.
With the k out front, something like that.
But then you would ask, what's the per capita growth rate?
Sure, that's a good question. What is the per capita growth rate? Well, so so I should say per capita growth rate at a particular value of t, or just in general? Okay, so that's a good question. Usually per capita growth rate is your rate of change divided by your population size. So I don't know if it's right, because again, I'm not seeing the exam exactly, but my best guess based on what we've written here would be to say it's equal to k times 1 minus n over 5,000. Just taking this equation and dividing both sides by n. Again, I don't know if that's exactly right, because I'm not seeing the exact question, but that's based on what you said, that's my best guess.
Would you say that, if you said, that if the population is less than 500 and go to 0, would that also be n minus 500?
Right, so yeah, so I think we probably need something, so like if we want to adjust it so that we have a minimum population of 500, I think it would be something like d and dt is equal to, assuming it's proportional still, k times probably n minus 500 times 1 minus n over 5,000. But honestly, the best way to check this is to draw the little graph of the phase plane. So if we draw the phase plane here, let's take a look and see. Let me ask everybody, based on just the equation I've written, what kind of typical graph shape should I have? Is there an M missing? So are we, but I don't know if I agree or not, because again, all right, I kind of turned this n into my n minus 500, because if this is if basically here you're saying 0 is kind of the lowest population you can have with this, and if I feel like we're changing that to 500, I think you don't want to, I don't think you want that n there as well. I think you want that. Again, I'm not 100% sure, but that's my best interpretation of it. So again, back to my question, if we're plotting dn dt versus n, what's the degree of this polynomial? Second, is it downward opening parabola or upward opening parabola? Right, because you have a positive n times a negative n. So we know it's going to be a downward opening parabola. The intercepts are going to be 500 and 5,000. So it's going to do something like this. So based on my picture here, is 500 the stable equilibrium, or is 5,000 the stable equilibrium? 5,000 is the stable equilibrium. So 500 is the unstable one. And yeah, if you're left of 500, if your population is less than 500, you're going to decrease down to 0. So my guess would be that this is probably correct, but that's just my guess. So not that we can't talk about the exam more, but talking about it without having it in our hands is not, there's not a lot of benefit to get like, you're like, okay, I think I did that one right, or I don't think I did that one right. Like, it's not like you can say really a lot more than that at this point. But yeah, I will say, are there any other questions pertaining to the exam you took yesterday? We'll be fine if there aren't. Yes, no, maybe.
Question one was like one of those comparison ones with the divergent and converted, is it smaller or bigger?
Oh, really? Okay, interesting.
It was 1 over 3x minus x squared and 1 over 3x squared
Oh, wait.
minus x.
sorry, so not this?
No, that is it. It was two, right? They're comparing them.
Oh, okay.
One's bigger, one's smaller. So that one was one, and then the other one is the same thing, but the 3x is also squared.
So we're looking at this, and we're also looking at the integral of what?
They just gave that integral, and then they gave 1/3x minus x squared, I think, greater than 1/3x squared minus.
So 1/3x minus x squared is greater than 1/,
3x squared. Minus x squared.
which is 1/2x squared.
I think also of the actual integral, the one there is square root.
Oh, yeah.
Mhm.
But for the comparison, it was
Yeah.
Sure, but I'm just gonna do this so I can. Right? And I'm assuming the limits of integration were something like 1 to infinity.
Yeah, something. Like that.
Okay,
Some number.
sure, it doesn't really matter what the bottom number is as long as it's not like. Actually, it probably needs to be starting at like 4. So if we start at 3, then you're dividing by 0, which is another problem. Hopefully it wasn't starting at 2. Oh, well, that's, and what was the question asking you to do? And okay, so, all right. I doubt. It's hard to use the comparison test when you have one of those where your integrand is undefined, so it's probably something like this. We'll go with it for a second. So if I know that my integral here, or my integrand is bigger than this, right? So I'll point out that this integral from 4 to infinity of 1 over the square root of 2x squared is just going to be the integral from 4 to infinity of 1/√2 times 1/x. That's going to diverge. We can write it as the limit as b goes to infinity. Let's just go ahead and do the integral. The 1/√2 hangs out. What's the integral of 1/x? Right, now ln of the absolute value of x. And then you have the integral from 4 to b. We plug in your limit of integration, you get the limit as b goes to infinity, 1/√2 natural log of b minus natural log of 4. And as b goes to infinity, the natural log of b also goes to infinity. So that goes to infinity, so we're certainly diverging to infinity. And then, since this integral is bigger than that integral, because that function is bigger than that function, because they told us it was, that one also diverges by comparison. Bigger than that. So it diverges. Again, assuming we have recalled it correctly. All right. Let's talk about first order linear differential equations. First order linear differential equations. I said it before, I'll say it again. When you're asked to solve a differential equation, you have one of two paths, and maybe both are an option. Usually they're not. Usually it's one way or the other. It's either going to be something that is separable or something that you can write as a first order linear differential equation. That's all we have. So if it's not separable, you know it's first order. If it's not first order, you know it's separable. If you're being asked to solve it, right? If you're being asked to do other things, you'd have totally other kinds of differential equations. But if you're being asked to solve, these are the only two methods of solving a differential equation that we have available to us in this class. All right, so let's look at an example. We have t times y prime is equal to 4y plus t to the 6 times e to the t squared. And it certainly does not look like it's separable. I've got my y prime over here. I could divide both sides by t, but there's no way of bringing that y over to the left-hand side just on its own without also leaving some y's behind on the right. If I divide both sides by y, I'd have to have t to the 6 times e to the t squared divided by y over there. So it's no go. So we're gonna try to write it as a first order linear. I'll remind you all, that means we're trying to write it as some y prime plus y times p of whatever your variable is, in this case, p of t equal to some other function of t, q of t. That's what we're trying to write it as. So we've got our y prime over here. We want to bring the 4y over as well. So we're going to have t times y prime minus 4 times y equal to t to the 6 times e to the t squared. And we're almost there. We're not quite there. We need y prime isolated. So we have to divide everything by t. So I'm going to write this as y prime, minus 4 over t times y equal to t to the 5th times e to the t squared. Now we're going to find our integrating factor. So our integrating factor which is called mu of t. He is calling it mu, right? He's not calling it I. Check. No, I don't have the thing. I thought that's right. Let me make sure I'm calling it the same thing. It's fine. Where did I put that? I had something. Oh well. It's gone now. So mu of t is going to equal e to the integral of p of t. dt. In this case, that's going to be e to the integral of what is our p of t? Negative 4 over t. So I would encourage all of you, when you do these problems, when you write this in the standard form on the left of the first order linear differential equation here, I would actually write this in the following way. Y prime plus, always a plus, always a plus. And then whatever's multiplying y, put it in parentheses. So negative 4 over t times y equal to t to the 5th, e to the t squared. It can be really, really easy to miss that minus sign on your p of t, and it's super duper vital that you don't. It really changes what your integrating factor is going to be. So here our integrating factor is going to be e to the integral of negative 4 over t dt, which is equal to e to the negative 4 times the natural log of t. We don't worry about the absolute value here. And then we should simplify this. It is always in our interest to make this look as simple as possible, typically by bringing up this negative 4 as the power of t, and you're going to get e to the natural log of t to the negative 4, and then e to the natural log of some stuff is just the stuff. So we end up getting t to the negative 4. If we had made the wrong choice and written our p of t as positive 4 over t, we would be getting t to the positive 4 as our integrating factor, which is totally different, right? It's going to make it would be wrong. We would end up being wrong. I don't recall how much work he wants you to show. Some people are totally fine with you jumping straight to the end and saying, great, our solution is going to be y of t equal to 1 over our mu of t times the integral of q of t times mu of t, which in this case would be 1 divided by t to the negative 4th times the integral of t to the 6th e to the t squared times t to the negative. Oh, what? I don't say every time I do this problem. Not t to the 6th, t to the 5th. Right? It's a t to the 5th times t to the negative 4. At least the first few times you do first order linear differential equations, I really think it's worth showing the extra steps about how we got to this solution. So the next step is to multiply everything by your integrating factor. We multiply everything by our mu of t, which is t to the negative 4th. Look what we get. We get t to the negative 4th times y prime plus t to the negative 4th times negative 4 over t times y equal to t to the negative 4th times t to the 5th times e to the t squared. Let's simplify that a bit. On the right-hand side, t to the negative 4th times t to the 5th is just t, and that's a good sign. We can see that when we're going to have to integrate that later, it's going to be really easy to do a u substitution. On the left-hand side, we have t to the negative 4th times y prime plus t to the negative fourth times negative 4 over t is going to be negative 4 times t to the negative fifth. Times y. As is true every time when we do this, the whole point is making the left-hand side look like the derivative of the product of y times mu. And this is exactly the derivative of t to the negative fourth times y. Product rule. You get t to the negative fourth times y prime plus the derivative of t to the negative fourth, which is negative 4 times t to the negative fifth times y. Every time. I can't say it enough. Every time. Still equals the same thing. And then we anti-differentiate both sides to get that t to the negative fourth times y is equal to the integral of t e to the t squared dt. And now you can kind of see how we're getting to here, right? We're dividing both sides by t to the negative fourth, and we're going to do the integral of t to the fifth times t to the negative fourth, which is t times e to the t squared. So that's how we're getting to that solution. Has he talked about for these problems if he wants you to show this much work or not? Right, it was like okay. So it's certainly good to be aware of what's happening. So let's wrap this one up. So here's the thing. I really would rather not write 1 over t to the negative fourth, right? It seems like a silly way to write that. It seems like it'd be much better to write it as, I think I can fit it in here actually, y equal to positive t to the fourth times the integral of t e to the t squared dt. We can integrate that. Again, I think you guys have enough experience at this point that you don't really need to show the use of here. I think you know that we're going to get t to the fourth times the integral of t e to the t squared is going to be almost e to the t squared. We're off by a little bit though. If you take the derivative of e to the t squared, you get e to the t squared times what? 2t. We almost have that. We just don't have the 2, so we need a 1/2 to account for that. And then it's super duper extra important that the plus c is in the parentheses that are getting multiplied by the 1 over mu of t out front here. So our solution here is that y of t is equal to, I'm gonna distribute all of it. I might not usually. It's going to be t to the fourth over 2 times e to the t squared plus c times t to the fourth. It is really important that c multiplies that 1 over your integrating factor thing. That's kind of the whole deal as far as doing first order linear. So I should say that's the whole deal, except that sometimes your mu of t is not as nice as this. This is a pretty nice mu of t here in this example. And sometimes your integral of mu of t times q of t is also more involved, right? It might be integration by parts, it might be substitution, it could be partial fractions, anything can really happen over there. Usually it's not too terrible, but usually, right? Doesn't mean all the time. So let's actually look at another example. I was going to look at that example from the practice exam that you posted that wasn't doable without doing this. There we go. Yep. I should pause it. Questions before we do this. All right, let's look at another one. So let's say we have the following differential equation. We have x squared times dy dx plus xy equal to x cubed plus 1. And again, it's almost already written in the usual way. And I'm gonna throw in this condition here, which hopefully I won't regret. Let's say that, let's be careful, James. Trying to think about things that won't be terrible. Let's say that y equals, I was probably gonna regret this, but oh well. Y equals 4 when x equals 1. Or you might write that as y of 1 equals 4. All right, let's go ahead and go through the process here. So first things first, it doesn't look like it's in the standard form. So I need to get dy dx or y prime all by itself. I will say for first order linear, I prefer to write it as y prime. For separable, I definitely prefer to write it as dy dx because we have to separate the y's and the x's. But here, I'd probably rewrite this as dividing everything by x squared, y prime plus x divided by x squared is 1 over x times y equal to x cubed divided by x squared is x. 1 divided by x squared is x to the negative second. Now, this one's kind of interesting. Yeah. I think we're good to go here. One thing I'll point out here is you definitely want to keep the y separate from whatever is being multiplied by it. Like I could have written this as y over x. That's not really a good move for me, right? I should write it as 1 over x times y. So then I can be like, oh yeah, there's my p of x. I do think it's not a bad idea to actually label the thing so you know what's what. So now we're going to find our mu of x. In fact, you all should find mu of x. I'll give you a minute. And simplify it as much as possible. All right. So mu of x is going to be e to the integral of 1 over x, which is going to be e to the natural log of x, which is going to be x. So let's actually jump straight to the solution and then we will maybe backtrack and show the work. Yeah, I always like it's hard for me to want to skip this part. I like showing this part, but we'll skip it. So skipping the work, we say great. Our solution y of t is going to equal 1 divided by x times the integral of our q times our mu. Okay, let's go ahead. Yeah, I'm glad I didn't pick x equal to 0. I think I would have been in trouble if I picked x equal to 0 from my initial condition. So now we're going to simplify this integral and then integrate it. So we're going to get 1 over x times the integral of x times x is x squared. X to the negative second times x is x to the negative first. As I've said many times, don't make the mistakes I made when I was a student. These x's don't get to cancel. You have to multiply this through and integrate before you can think about multiplying this through and dividing or canceling stuff. All right, this is not written in my favorite way, but fine. I'm going to get 1 over x times the integral of x squared is x cubed over 3. The integral of x to the negative 1, I would have rather written that as 1 over x. So that I know that my integral is the natural log of. Do I want the absolute value here? I think I kind of do. Normally, I would say you don't need the absolute value here. I won't say it's exceptional because it's not just the absolute, but natural log of absolute value. So I don't know. It's kind of, yeah, I guess I need that there. Plus c. I personally prefer to distribute this 1 over x or 1 over whatever it is. I think it looks better. It's probably not actually necessary. So you can write it like this, or you could write it as, oh, and why am I writing y of t? Because I'm a fool, that's why. It's y of x. Or we can write it as y of x equals x squared over 3 plus the natural log of the absolute value of x over x plus c divided by x. And now our job is to figure out what C is, because we have an initial condition. So we're going to plug in x equal to 1 and y equal to 4. So we're going to get 4 equal to 1/3 plus 0 divided by 1 plus C divided by 1. So it looks like C is going to equal 4 minus 1/3. Or if you prefer, 11/3. You would like to maybe see that. If you get to this stage, you're not done. Technically, you found all the things you need to find, but you really, really, really need to write your final answer as the function. So our solution here is that y, or y of x, is equal to x squared over 3 plus the natural log of the absolute value of x divided by x plus 11/3 divided by x. So I think it's totally fine to skip the intermediate steps that we're about to go back and fill in, as long as your instructor is fine with that. Here are the steps we skipped though, just so you can see them. So the next step here after finding the integrating factor is to multiply everything by the integrating factor. When I say everything, what I really mean is I'm thinking of all three pieces, both sides. So I'm going to have x times y prime plus x times 1 over x is just y. You could write 1 times y if you wanted to. On the right-hand side, I'm going to have x times x plus x to the negative cube. The left-hand side is always the derivative of the product. And you can actually be more specific. It's not just any product. It's always the product of your integrating factor times y. So it's going to be the product of x times y. Or another way to see that easily, if you have to do these intermediate steps, is if you look at whatever, if you look at your x times y prime, you can just like throw parentheses around that and move the prime on the outside. It always works. It worked. Like if you look back at our previous example, if you look at my t to the negative 4th times just y prime, you can think about putting parentheses around that and saying, oh yeah, it's t to the negative 4th times y all prime. It works every time. And then we would have equal to, if I distribute this here, x squared plus x to the negative 1st. And then if we integrate both sides, we get x times y equal to the integral of x squared plus x to the negative 1st. And then divide both sides by x, and oh yeah, we're right there. So that's why it's totally okay to skip those steps, because you always end up in the same place, where it's your solution is 1 divided by your integrating factor times the integral of q times your integrating factor every time. All right. So yeah. What I would say about this is, if you're just given an equation, not a big deal, right? You can kind of make it work. Usually you can identify whether it's separable or first order without too much effort. But a lot of these problems are going to be word problems. Tank problems abound. There's also some other like Newton's law of cooling type problems where they're giving you a bunch of words and you have to interpret it. Let's start off with the tank problem, because the tank problems are usually pretty straightforward. So here's a tank problem. And actually, well, yeah, I like this question. So we'll do this whole thing. So that's number 3. The tank initially contains 100 gallons of solution with 10 pounds of salt. A solution containing, I don't like containing there, a solution with a concentration of 2 pounds of salt per gallon is added to the tank at a rate of 4 gallons per minute. As always, the well-stirred mixture, it has to be well stirred, otherwise you're gonna have problems. Is drained at, and this is actually the most important part probably, whether it's at the same rate or at a different rate. In this one, we're gonna do the same rate. And then maybe we'll do another one where it's a different rate. At the same rate, which is 4 gallons per minute. Okay. If that word occurs there, the same rate, or where they tell us it's the same number drained out at the same speed, that means you can actually solve this either by doing a first order linear or by doing it as a separable differential equation. We're going to do it both ways in the hope that I can convince you that doing it as a first order linear is actually the easier way of doing it. I will tell you, I have come a long way around to this point of view. I used to always think it was better to do it as a separable differential equation because separable just always felt easier. I have changed my mind. I think it's computationally easier to do as a first order linear, but we'll see that as we do it. But before we can do any of that, we have to set it up. So we have our tank here, and it contains 100 gallons of solution with 10 pounds of salt. And then into the tank we're putting in a 2 pound per gallon concentration at a rate of 4 gallons per minute. Here's the fun part. Going out, the concentration is not 10 pounds per 100 gallon. It's whatever we're going to call the amount of salt, which is going to be S of T typically. So it's S of T pounds of salt per 100 gallons of volume. Because the volume isn't changing because we're putting in 4 gallons every minute and we're taking out 4 gallons every minute. If it was changing, that denominator would be a little more complicated. Multiplied by the 4 gallons per minute that we are taking out. So we can say that our differential equation ds dt is equal to the rate in minus the rate. I feel like rate's the bad word. The amount in minus the amount out. So it's going to be 8 pounds per minute going in, right? 2 times 4 minus S over 100 times 4 going out. All right. So now let's do this. Which way do I want to do this first? Let's do it separation first. I feel like we did this one last time. Maybe I'm thinking about a different class. So if I want to separate, I'm going to write this as, I only have S's over here. So first of all, I would probably rewrite this part here as S over 25. Because 4 over 100 is 1 over 25. And you have a choice, and I don't want to make the wrong choice. So I don't want to make the choice that's going to make my life harder. So here's one way you could do this, which we're not going to do. We could write this as 8 minus S over 25, and then just divide the whole left side by 8 minus S over 25. That's not going to be super convenient for us. We don't want to do ds divided by 8 minus S over 25 equal to 1 times dt. It would work. You can totally do it this way. Not the best. Instead, what I should really do is multiply the top and bottom by 25 and then divide the 25 over here, or kind of cutting that off at the pass, getting a common denominator over here. So saying that ds dt is equal to, let's see, 8 times 25 is 2 times 4 times 25, which is 2 times 100, which is 200. That's going to be 200 over 25 minus S over 25. And now I'm going to separate this by dividing both sides by 200 minus S and multiplying both sides by dt. So I end up getting that ds divided by 200 minus S is equal to 1 over 25 times dt. Then we're going to integrate both sides. We have the integral of 1 over 200 minus S ds is equal to the integral of 1 over 25 dt plus 2. Integrating the left-hand side, I want everyone to do the integration on their own. Integrate both sides. Careful with the left-hand side. There's an extra little thing you have to think about. The right-hand side for you. Left-hand side is going to be the negative natural log of 200 minus s. And I'll talk about it again, but I'm not going to write down. We've talked about how we can ignore the absolute value here. We don't need to worry about it because it's going to get dealt with when we do the plus or minus e to the c, essentially. So we're okay. Solving, here's what we're going to get. Multiply both sides by -1. We have the natural log of 200 minus s equal to -1/25 times t. -1 times a constant, still a constant. I'm going to write plus c. Now we're going to exponentiate both sides. We're going to get e to the natural log of 200 minus s equal to e to the -1/25t plus c. Simplifying both sides, the left-hand side, we get 200 minus s. The right-hand side, I really don't like writing out these steps twice. It's going to be e to the -1/25t times e to the c, which I'm just going to call a. Which we usually write in front, but I didn't have enough room. And then we're going to solve for s. So we're going to get s equal to 200 minus a e to the -1/25t. So s, or s of t, equals 200 minus a e to the 1/25t. Lastly, plugging in our initial conditions. I really feel like we did this one before, but oh well, it's not bad to see it again. Plugging in our initial conditions, if I plug in 0 for t and 10 for s, I have 10 equal to 200 minus a. So a has to end up equaling 190. So you end up getting that our solution is s of t equals 200 minus 190 e to the 1/25t. I know I didn't show my work there for that part, I just said it. But I think you all can see it, right? If we plug in the 0 for t and 10 for s, we get 10 equal to 200 minus a, so a has to equal 190. All right, let's do it again. But the other way. I feel like this is a lot of terrible thing. This is more algebra than I want to have to do. Than I want you, really, I don't care. I can do all the algebra I want. This is more algebra than I want you to have to do, right? I think the first order linear way of doing this is going to be easier computationally. So let's actually do it that way and see. Yeah. Good question. I think you know what? I think I might have actually lost that. Good call. I did lose the negative. Yeah, excellent point. Thank you for catching that. Yeah. Let's explore that for just another moment. So, do I want to explore that right now? Yeah, I do. So if that had been a positive number, 1/25, what would happen as time went on and on and on? Well, either the positive 1/25 times t would get larger and larger and larger. We get infinitely large, which means the amount of salt would get to be 200 minus 190 times a larger and larger and larger number, which means the amount of salt would eventually be negative, which wouldn't make any sense. On the other hand, and this is actually what I think is really interesting about this, written correctly, if you let time go on and on and on, the amount of, well, this part here, the e to the -1/25t gets closer and closer to what? 0. So the amount of salt gets closer and closer to 200 minus 0, which might not sound interesting at the moment, but how much volume is in the tank? So if the amount of salt is getting closer to 200 pounds and the volume is always 100 gallons, what is the concentration getting closer and closer to? Well, 200 pounds divided by 100 gallons, it reduces to 2 pounds per gallon. The concentration of the thing we are adding in, that is not a coincidence. That is very much something that happens. If you keep adding in something that has a specific concentration and you drain out at the same rate, it does have to be the same rate, otherwise it doesn't work. Eventually, the thing in the tank gets closer and closer and closer to the concentration of the thing you're adding to it. If you let time go on forever. Question. Yes. I plugged in the initial condition here, which I didn't write down, but my initial condition was that at time equal to 0, the salt was equal to 10. That's what I plugged in. Which I knew because they told me at the beginning of this process there were 10 pounds of salt in the tank. All right, let's do it the other way. We're going to take our same differential equation. We're going to do it as a first order linear now. Sorry, differential equation ds dt equal to 8 minus, let's write it as s over 25. And now we're going to write it as a first order linear. So we're going to bring the s over 25 to the left side. So we're going to rewrite this as, I'm going to write it as s prime plus s over 25, or 1 over 25 times s equal to 8. Well, this doesn't seem too terrible. So let's find our integrating factor. Our mu of t is going to equal e to the integral of 1 over 25. And you know what I didn't do, which I should do? Again, not a huge deal, but I think it's worth your while to remind yourselves what p of t and q of t are. They're not very exciting here. They're both constants. That's okay. It's actually kind of great. So if we integrate this, it's just going to be e to the 1 over 25 times t, or t over 25 if you prefer. And then we're going to multiply everything by that. So we're going to have e to the 1 over 25 times t times s prime plus e to the 1 over 25 times t times 1 over 25 times s equal to 8 times e to the 1 over 25 times t. As is always the case, the left-hand side is just the derivative of a product. This is just the derivative of e to the 1 over 25 times t times s. Check it out, right? You leave the first thing alone, multiply by the derivative of the second thing, plus you take the derivative of the first thing, which is e to the stuff, times the derivative of the stuff. That's where the 1 over 25 is coming from. Multiply by the not derivative of the other piece. Hopefully I've said it enough times. The left-hand side is always the derivative of the product of your function times your integrating factor every time. So then we're going to say that e to the 1 over 25t times s is equal to the integral of 8 e to the 1 over 25 times t dt. Integrating both sides and multiplying both sides by e to the negative 1 over 25t. And I would rather write e to the negative 1 over 25 times t as opposed to 1 divided by e to the positive 1 over 25 times t. They're the same thing. So we're going to get the s, or s of t, is equal to e to the negative 1 over 25 times t times the integral of 8e to the 1 over 25 times t, which is going to be 8e to the 1 over 25 times t divided by what? Right, which is multiplying by 25. I'll write divided by 1 over 25. Plus c. All right, let's distribute. Well, let's simplify and distribute. So we're going to get, let's see, 1 over 25, or I should say 8 times 25 is, once again, 200. So we're going to get the s of t is equal to 200. The e to the negative 1 over 25t times e to the positive 1 over 25t multiplies to e to the 0, which is 1. And then you have c times e to the negative 1 over 25t. And then plugging in our initial condition that time equals 0 and s equals 10, we get 10 equal to 200 plus c e to the negative 1 over 25 times 0, which means that 10 is equal to 200 plus c, so c had better equal negative 190. And then our final solution ends up being s of t equal to 200 minus 190 e to the negative 1 over 25 times t. The same. Sorry, you can't see both. But they're the same. So I think this was much easier personally. There was a lot less. Well, first of all, you'd have to deal with integrating something, getting the negative natural log of whatever. The integration is much easier. I don't know. I think if you have the choice, like if your differential equation is such that you can choose, which is not often, but will always be true if your tank problem is the same rate in, the same rate out, I think you should choose first order linear with an integrating factor. I think it's just the easier way to do it. It's less computationally complicated. And then you might be asked questions like, how much salt is in the tank after an hour, or how long does it take until there's 30 pounds of salt in the tank, or lots of questions you can ask. But right, that's not really that interesting, right? Because then you're just either setting time equal to something or setting the salt equal to something and solving for time. It's pretty straightforward. It's like solving it's like when we had exponential growth and decay problems, the same sort of idea where you're setting either the amount equal to something and solving for time, or setting the time equal to something and solving for the amount. I see faces that look like there might be questions. Are there any questions?
It became negative because you divided.
What became negative? Oh, yeah. Well, right. Yeah. To get from here to there, I divided both sides by e to the 1 over 25t, but I would rather write e to the negative 1 over 25t as opposed to 1 divided by e to the 25 over t. 1 over 20. Oh my gosh, e to the 1 over 25 times t. So many words. Okay. Let's do another one where the rate in and the rate out are not the same. Those are a little bit more complicated. Okay. Let's oh, come back. All right, let's see here. 1 second. I had a problem. So another question. I think this is number 4. Writing using numbers. So we're going to say let S of t be the amount in pounds of sugar in tank at time t. See where we're measured time in minutes. It is important in these questions to pay attention to the unit of time, because occasionally they'll do something terrible, like say time is measured in minutes and then ask you something about how time being an hour later or something. So make sure you're using the same units of time whenever you're doing these problems and converting if you need to. A solution with a concentration, I really think containing just isn't the right word there. Concentration, if I can spell it, of 3 pounds of sugar per gallon begins flowing into the tank at a rate of 4 gallons per minute. If the well-stirred mixture, always well-stirred, someone's doing that stirring, is drained at a rate of 6 gallons per minute, and the tank initially holds 400 gallons with 50 pounds of sugar, What are we making? That's not the question we're gonna ask. Set up the differential equation, right? That'd be funny. Like, what are we making? Good question. Sugar water. Okay. So really the question, so kind of the most typical way someone might ask this question is, so if all this is true, how much sugar is in the tank after 1 hour? Which, without saying it, says set up the differential equation, solve the differential equation, and then finally, after you've done both those things, plug in time equal to 60 minutes to figure out how much sugar is in the tank. Okay, so we got to set the differential equation. So I like drawing a little picture of the tank. I find it helpful. I don't know why, I just do. Into the tank goes sugar at a concentration of 3 pounds per gallon at a rate of 4 gallons per minute. The reason I like writing the units here, especially, is to make sure that the thing going in the units work, right? I'm putting in sugar at a rate of 3 times 4, 12 pounds per minute, because the gallons are going to cancel. I like seeing that the gallons are going to cancel better. Similarly, on the way out, so our concentration is going to be a little bit dicier, right? And in the tank, we're starting with 400 gallons and 50 pounds of sugar. But we're taking out volume, right? We're putting in 4 gallons every minute. We're taking out 6 gallons every minute. So the rate going out is 6 gallons per minute. But the concentration of the solution is changing, both in the amount of sugar, which is just S of T, but the volume isn't a constant anymore. It's not 400 gallons the whole time. It's actually decreasing, right? Every minute we're losing 2 gallons of solution. So it's going to be 400 gallons minus 2 times T. Also, kind of interesting, especially when you're losing volume, you can be asked something about like how long this process can go on for. We can only sustain this process for 200 minutes, right? And then we're out of volume. So maybe worth noting, sometimes people ask about that just as a kind of a common sense check. All right, so let's set it up. I mean, really, we've already set it up, right? Your job now is just to write the differential equation, that minus that. That's the whole setup, right? ds dt is equal to 3 times 4 minus 6 times s over 400 minus 2t. What do you do? We cannot do this as a separable differential equation. Cannot? No, we cannot. Because if we want to separate, we'd have to kind of get the common denominator on the right hand side. But then both your denominator will have t's and your numerator will have t's and s's, and you can't really get that numerator on the left or the right side and have just like you're stuck. But more generally, if you just as a blanket statement, if your rate in is different than your rate out, you cannot do it as separable. You have to use the first order linear. Great. It's nice not to have choices sometimes. Sometimes it's terrible. So we're going to rewrite this so we can do it as a first order linear. And I'm going to make one simplification here. I'm going to say that ds. Oh, darn. Oh well. It's not really darn, but I wanted something to happen that's not going to happen now because I'm going to simplify it. Yeah, we should simplify it. So here's what I wanted to see. I wanted to see that when we integrated 1 over 400 minus 2t, we got the natural log of the absolute value of 400 minus 2t, and then I had to divide by -2. But I'm going to actually simplify this in a way that I don't have to. So I'm going to write this as plus 6 over 400 minus 2t times s equal to 12. And then we can reduce this to 3 over 200 minus t, right? We can totally divide the top and bottom by 2 and rewrite this as ds dt plus 3 divided by 200 minus t times s is equal to 12. So it's usually worthwhile to do easy simplifications like that. They make your integration easier. All right, I want everyone to find the integrating factor. and simplify it as much as you are capable of. So there's what I got. E to the integral of 3 over 200 minus t, which is e to the negative 3 times natural log of 200 minus t. Now we can simplify this further, and we should. So this is going to be e to the natural log of 200 minus t to the negative third, and then we can rewrite that as 200 minus t to the negative third. Or it might be preferable, and again, might be, so I'm just writing it down so I see it. We can write it as 1 over 200 minus t cubed. But probably the first way. All right. How much work do we want to show? Do we want to show all the steps? Not really. So reminder, if you don't want to show all the steps, that's fine, but you have to, well, probably fine, but you have to know what the end result is. So, right, we know that our solution here is going to be that S of t is equal to 1 over mu of t times the integral of q of t times mu of t. So seeing that, I probably do a couple things. So I'm going to say that my S of t is going to equal, well, here's my mu of t. 1 over that is just going to be 200 minus t to the third power. So I have 200 minus t to the third power times the integral. Q is just 12. Now here I would want to write my mu of t not that way, but that way, so it's easier to integrate. So it's going to be 12 times 200 minus t to the negative third dt. Let's integrate. It would still be negative, right? Because, right, so this, right, this right here, that's your 1 over mu of t. So 1 over 200 minus t to the negative third is the same as 200 minus t to the positive third. But here, this is just your mu of t, not adulterated. What's that? Where? No. So this one, yes. This one, no. Because this is so you could say this is the same as 1 over 200 minus t to the negative third. But if I bring it up to the numerator, that changes the sign of the exponent. Right, this is the same as 200 minus t to the positive third, which is why I'm writing it like that. That makes sense? I feel like so I like, right, this is my mu of t. It's either this or it's this. Right? Either way is fine to write it, but they are different. So I have to choose. And I guess I didn't really write either one of them because I said, well, if mu of t is equal to this, then 1 over mu of t is the reciprocal of that, which is just 200 minus t to the third power. Yeah, because that's accurate though. That is mu of t, but I'm not writing mu of t here. I'm writing 1 over mu of t, and then I simplified it. So, right, we could have said 1 over mu of t is 1 over 200 minus t to the negative third, but then I wanted to write it in a simpler way. So then we're going to integrate. The 200 minus t to the negative third is going to hang out in front. Sorry, 200 minus t to the positive third. It's going to hang out in front. And then the 12 we can also pull out in front. And then the integral of 200 minus t to the negative third is going to be, we don't need to use the substitution here, although we could. It's going to be 200 minus t to the negative second divided by negative 2, also divided by negative 1 because of the negative on the t there. So let's just divide by positive 2 plus c. I would probably distribute. Yeah, I like distributing here. So distributing. Yeah, so check this out. We're going to distribute this to each term. And we're going to have, so 12 divided by 2 is 6. So we're going to have S of t equal to 6 times 200 minus t to the first plus, I probably wouldn't usually write it this way, but I'm going to write it as 12 times c times 200 minus t cubed. Although really, we could have said 12 times c is just a new constant. Because when we solve for our constant here, so let's pretend like we solve for the constant and we ended up getting that c was equal to 5. Am I going to write 12 times 5? No, I'm going to write 6. Right, so it kind of would make more sense to call this whole thing a new constant, but you don't have to if that feels. So then we're going to plug in our initial conditions, which were that when time is equal to 0, the amount of sugar, I think I've been saying salt for a while, but it is sugar, it doesn't really matter. The amount of sugar was 50 pounds. Right, they told us in the beginning in the tank there were 50 pounds of sugar. So then we're going to plug in 50 for S, 0 for T. And then we're going to solve for C. So let's see. 6 times 200 is 1200. 50 minus 1200 is negative 1150 equal to 12 times C times 200 cubed. So I'm going to stop at where I think is best. I'm going to say negative 1150 divided by 200 cubed, which is kind of huge, is equal to 12C. Yeah, I could go ahead and solve for C, but then I just end up multiplying it by 12 anyway, so why bother? So then I'm going to plug in this value for my 12C right there. So my solution is that S of t is equal to 6 times 200 minus t, and I don't think there's any good reason to multiply that out, plus this number. So let's write it as minus 1150 over 200 cubed times 200 minus t cubed. One sec. So I'll point out that if we plugged in time equal to 0, we would get a value of S equal to 50. If you plug in 0 for t, you're going to get 6 times 200 minus, I feel like I'm making a small mistake here. Let me double check something here. No, that's right. Yeah, I'm just wrong. I'm just losing my mind. If you plug in 0 for t, you're going to get 200 cubed divided by 200 cubed, which cancels out to 1. And then you're going to get 6 times 200, which is 1200, minus 1150, which is going to give you 50. You have a question, Jennifer?
So the 2 disappears and I see a 6, so how do we split up the 12?
Because 12 divided by 2 is going to give me that 6.
Yeah.
And then 12, but the 12 doesn't get divided by 2 and you multiply it here. So I'm multiplying this whole thing, I'm distributing that whole thing to each piece. So the first piece is 12 times 200 minus t cubed times 200 minus t to the negative second divided by 2. The 200 minus t to the third times 200 minus t to the negative second, those powers add up to positive 1. And the 12 times 1/2 gives me the 6. These problems are kind of the worst. Like often we don't solve tank problems that are this challenging because they're just kind of grody. But sometimes teachers will have to do them. All right. Other questions? Oh, I guess so. Then Right, exactly. I don't really care about the question I asked, but to answer the final question, how much sugar is there in the tank after an hour? We wait, cool. So S of 60 is going to be 6 times 200 minus 60 minus 1,150 divided by 200 cubed times 200 minus 60 cubed. Whatever that number ends up equaling, which is terrible. Not the point of the question, really. But a good way of avoiding having to write the words, find the differential equation and solve the differential equation. If you have to find how much salt is in the tank or sugar is in the tank at a particular time, you know you have to do those other pieces first. All right. What time is it? It's 11:38. Let's call it a day.